So the next theorem in this section is similar to the previous theorem. It just generalizes things a little bit. Let's switch our lasers. So again, I have two sets, x and y. I'm thinking about x as the domain of my function, y as its codomain. And now this time, this is different. Instead of having two sets, a and b, subset of x, and two subsets of y, I'm going to have an arbitrary collection, f. F is an arbitrary collection of subsets of x. Y is an arbitrary collection of subsets of y. And here's what you can say. The preimage of the union of an arbitrary union of sets in y is the union of the preimage of those sets. So again, the preimage behaves super nice. It's great. Similarly, the preimage of the intersection of a bunch of arbitrary collection of subsets R and Y is the intersection of all those the preimage of all those sets. The image behaves nicely over unions, but not over intersections. The image of the union of a bunch of sets, an arbitrary collection of sets in X, is the same as the union of the image of those sets. And then you have the same containment, but not equals, for the image of a bunch of intersections, and the intersection of an arbitrary collection of sets. So we're going to want to understand this result, and we're going to need to be able to reference it. I thought that I would prove some of these, and then in the homework you're going to be asked to prove the other parts. So I'll prove one just to get you going, and then I'll leave the other three parts for you. So let's prove part A together. So let's realize again that I can do the equalities here. I don't necessarily have to try to show containment both ways. You can. I'm going to do both containments as an if and only if as I go along. It's the same thing actually. So X is in the preimage of the union of all of these sets C and R if and only if f of x itself lands in the union of this collection of sets. Okay? But you then realize, well, wait a minute, that happens if and only if there's f of x is in this union, if and only if x is in at least one of these c's. So f of x actually lives in C for some C in R. Okay, but then if f of x lives in C, then that happens if and only if x is in the preimage of C for some C in R. And then you say, okay, wait a minute, if x is in the preimage for some C, then at this point this is an if and only if x is in the union over all C in R of the preimage of C. So it's if you're in the union, you are in the union if and only if you're in exactly at least one of them. And so at that point, I'm actually done. I've shown you that if x is in here, then x is in there, and it's actually if and only if. You could do containment both ways. You would start here and go down, and then you would start here and go back, and it's the same argument. So you are allowed to combine them when they are if and only if every step. So for the proof, we'll just say that the other parts are left as homework. And we'll leave it at that. So I'd like you guys to do 2, 5, and 6 from 3.2, and then I believe I assigned the other problems. Here they are, 1 and 3 from 3.1, and I'll put the due date on the homework list. All right.